Let's take a look here at the mathematics behind a double slit experiment interference pattern. So as you saw in the previous video about Young's double slit experiment, when light wave enters two narrow slits, you get an interference pattern on the screen that looks like a bunch of different areas of high intensity and low intensity. We call those areas that are bright fringes or dark fringes, or areas of maximum and minimum. We denote the areas of maximum with the variable m, and the one in the middle is m equals 0, and then we count up m equals 1, 2, 3, etc., or m equals -1, -2, -3. It really doesn't matter what order you're going in because the interference pattern is symmetrical about both sides. We also have areas of dark fringes or dark spots or minimum, and those are denoted by the letter n, and those are here on the peaks and valleys. These would be the valleys. So we would have n equals 3 and this position, or -3 to follow the same pattern above, n equals -2, n equals -1, etc., etc., and then counting up 1, 2, 3 on the other end. You can see here that there's no n equals 0 value, unlike the maximum where the central max is m equals 0. Another important part here is the width of the slits. So we have two narrow slits at the end. These are either denoted by the variable w for width or d for distance. We're going to stick with d, although you might see w in some other references or other examples. You can see we also have the distance from the slits to the screen, and that's denoted L. We have the angle from the central maximum to whichever peak you're looking at as theta, and that's in here, that's the angle. And then we also have the distance between the first maximum and the central max labeled as x1. Now we're going to work a little bit with that in just a second. We have an ability here to calculate or determine the wavelengths as a function of whether or not you're looking at a destructive or a constructive area of interference. What's really important here is the equations. And so the equations that we come up with are all rooted in trigonometry. You may recall from our previous lessons the discussion of path length difference. And when you have a double slit, so you have source 1 and then source 2, we recall that we have what we call a path length difference. So if we're looking at a screen somewhere on the right hand side here and some constructive interference point, let's say M1, although the actual value doesn't really matter, we can see that there's a difference in the path lengths it takes to get from S2 to M1 and S1 to M1. Well, this distance here is known as D, or W for the width, and we can also form a right-angled triangle where we have some angle theta in here, which is equivalent to the angle theta that you see in the previous picture. Given this, and given the path length difference, which we're going to call delta L, we have a right angle triangle that we have variables that correlate with the sine trig ratio, right? If sine equals theta, or sine theta, sorry, equals opposite over hypotenuse, we have the opposite being delta L, and the hypotenuse being the slit width. Well, that path length difference, delta L, is going to be equal to m lambda. It's going to be equal to whatever the peak you're looking at is the first peak or the second peak or the third peak away from the central maximum, times the wavelength. Because this is constructive interference, every path length difference has to be a multiple of the wavelength of the light, or whatever the wave is in this case. After making that determination, we can do a little bit of substitution to figure out what our equation would be to solve for that wavelength given both constructive and then destructive interference. So let's focus on the situation where we're looking at constructive interference. And we had just said that sine theta equals delta L over D. Sine theta equals delta L over D. Oops, sorry. Where delta L is equal to m lambda, and I'm going to bring d over to the other side. This is typically the format that we see this equation in, although of course we could substitute m lambda here and use the equation this way if we're looking at it from more of a pure trig point of view where we're solving for the angle. To take a look at how this changes with respect to destructive interference, all we have to do, destructive, is recall that the difference between a constructive interference pattern and a destructive interference pattern is simply half of a wavelength shift. And so this leaves us with either d sine theta equals m plus 1/2 lambda, or d sine theta is n minus 1/2 lambda if we're going in the other direction. So either of those equations is going to work fine. It just depends on what you're given. So if you're given a variable relative to a bright fringe, you're using m, and if you're given it relative to a dark fringe or a dark spot, you're using n. M can be any whole number value, positive or negative, and 0, and n is a whole number value excluding 0, both positive and negative. One last assumption, or one last kind of trick we're going to take a look at here to make future problems a little bit easier, is that in the situation where the screen is sufficiently far from the slit, so we have our screen kind of going this way with length L, we have the distance from the central maximum m equals 0 to the first maximum x, or m equals 1, and we'll call that difference x1. And of course we have whatever the hypotenuse is here to complete this right angle triangle, and our theta 1. Normally you would look at this, and the only trig ratio that would come to mind would be the tan ratio. And we would say tan theta 1 is opposite over adjacent. However, in the situation where L is extremely long, then that long side becomes pretty much equal to the hypotenuse in terms of value. And we make the approximation that sine theta is approximately equal to tan theta. And this allows us to use the two equations we came up with before, or three I guess, for constructive and destructive interference, to be able to calculate other properties based on other variables that are given depending on the question you're dealing with. So if we then substitute sine theta for tan theta, making the assumption that they're pretty much equal, we'll say something like sine theta 1 equals x1 over L. And we can rearrange this to say x1 is L times sine theta 1. Now by manipulating the constructive interference question, we see that sine theta is m, which is 1 in this case, times lambda over d, which then allows us to take this equation one step further and say L lambda over d. And this works if and only if you're referring to the first bright fringe relative to the central maximum. Well, what if I'm not doing that? What if I'm referring to any fringe that I want? Then all we need to do is reintroduce our m variable. So we would say ml lambda over d. And in the situation where you're not referencing the central maximum at all, say I want to know the difference between m1 and m2, or m5 and m6, or m-2 and -3. What we're looking at here is the distance between any two bright fringes, which we're going to call delta x, is equal to L lambda over d. We don't need the m because, of course, the distance between any pair of bright fringes that are adjacent to each other should all be the same. Let's take a look now at a really quick example so we can make use of some of these variables and see how the equations are applied in a more productive context. So let's determine the separation between bright fringes. So remember, the separation between any two bright fringes is going to be delta x. There's no subscript here because we don't care if it's between 1 and 2 or 2 and 3 or 3 and 4 because they're all going to be the same. And that is created by a red laser light with a wavelength of 630 nanometers. The slit separation is 0.1 millimeters, and the distance from the screen to the slit is 0.5 meters. So the slit separation, this is our value for D, and the distance from the screen to the slits, that is our value for L. Now it's really important to first realize that all my units here are different. So that's not going to work for us. We need to rewrite these variables in any measurement unit. It doesn't matter as long as you pick the same one. I'm going to put everything into meters. So the wavelength is going to go from 630 nanometers to 6.30 times 10 to the negative 7 meters. The slit width separation D is 0.1 millimeters. So we're going to call that 0.1 times 10 to the negative 3 meters. I know that's not in scientific notation, but frankly it doesn't really matter. And then the slit, or the length, sorry, the distance from the screen to the slit will leave exactly as it is. And what we're looking for is delta x. The hardest part of these questions is really identifying what it is that you're looking for and what variables you have, and then taking it one step further to try to identify the equation. So if I were to flip back to my previous note, I would see that this is probably my best bet, L lambda over D, because I have all of this information. So the length from the screen to the slit is 0.5 meters. The lambda value is 6.30 times 10 to the negative 7 meters. And the slit width, or the distance between S1 and S2, is 0.1 times 10 to the negative 3 meters. So it's important that everything here is done in meters. Any two of the numerators will cancel with the denominator, and our answer is going to be returned to us in meters as well. So our answer here ends up being 3.2 times 10 to the negative 3 meters. I would probably rewrite this in more useful units. In this case, we would say 3.2 millimeters. So that's the distance between any two bright fringes. So if we have our setup that looks like this, and we have our central maximum here with m equals 0, and then the first one, m equals 1, becomes this way, m equals negative 1 comes down over there, m equals 2 is up here, m equals negative 2 is down here. The distance between any two adjacent fringes, so 1 and 2, 0 and 1, negative 1 and 0, or negative 2 and negative 1, these distances are all going to be delta x, which is 3.2 millimeters. Let's try another example now with a little bit of different information. So we're going to end up using a different equation, of course. So we're going to pass light from helium neon laser through two slits that are separated by 0.01 millimeters, and we find a third bright line on the screen which forms an angle of 10.95 relative to the incident beam. That means relative to m equals 0. What's the wavelength of light? So, it might help to draw a picture here just to see what's happening. So we have our slits, S1 and S2. We have our screen over here. And this would be the central beam, which produces m equals 0. We obviously have m equals 1 and m equals 2, but they're not relevant for this question because I don't have any information about them. What I do have information about is m equals 3. And I'm told that there is some angle here produced, theta 3, that has a value of 10.95 degrees. So what's given to me? I'm given the slit width, which I'm going to rewrite in meters. Again, this isn't in scientific notation, but it still works. I'm given the angle theta, 10.95, and I've said theta 3 there just so I know that it's at the third bright fringe. And I'm given the value of m, which is 3. Now, of course, you're going to get the same answer if you had negative 3, right? It wouldn't really make a difference here. So we're going to pull the first equation we actually came up with, which is d sine theta equals m lambda, because I have the slit width d, I have the location m3, and I have the angle 10.95, and I'm looking for lambda. So quickly rearranging this, I'm left with lambda, and then is equal to d sine theta over m. So that gives me 0.0100 times 10 to the negative 3 meters, sine of 10.95 degrees, all divided by 3. This will leave me with 6.33 times 10 to the negative 7 meters. That's probably how your calculator is going to spit it out. It'll give you an answer in scientific notation. That answer is fine, but for light, we know we're in nanometers typically, especially for visible light. So it might make more sense to convert this to 633 nanometers. Next up, let's take a look at solving for the number of possible bright fringes or maxima. So this question asks us the interference pattern, it asks us that interference patterns do not have an infinite number of lines. There is a finite number of bright spots and dark spots that you will see. There is a limit to how big M can be. So what is the highest order constructive interference possible within the system described in the previous example? So let's recall what we had in the previous question. We had a slit width of 0.0100 times 10 to the negative 3 meters. We had a wavelength that we solved for of 6.33 times 10 to the negative 7 meters. I know I reported it in nanometers before, but we're going to have to convert back to meters anyway, so we may as well do that now. We had we're looking for M. We're looking for the maximum number of bright spots. And the angle previously wouldn't be useful here. So I'm looking for the total number of bright spots, and to do that I first need to deduce to myself when might the largest or the furthest bright spot occur. And I have to take a look at what it means to have a sine of an angle involved in my question. So sine produces a maximum. The sine function produces a maximum at sine is 90. That produces a value of 1, and that's the maximum value that the sine function can return. Now, sine function is also repetitive, so I'm going to get that maximum value of 1 at several other points. So as you can imagine, our bright fringes won't go on forever because the sine function is repetitive, so there will be a maximum value it can hit, and that's going to be 1. So what we'll say here is that we will get the last bright fringe at or around theta equals 90. So by rearranging the equation above, we can say that M, the value of the furthest bright fringe, is d sine theta over lambda. And by substituting all my values from before, 0.01, sine theta of 90, so sine 90 is always equal to 1, and then divide by the wavelength that we discovered, will give us a value of 15.8. What that means is that in our situation, the furthest fringe, wherever that ends up, the furthest bright spot, is going to be at M equals 15, not 15.8 and not 16. So we have to always round down here because 16 would be too big. It'd be off of our scale. That would have an angle of greater than, or actually wouldn't be possible because once we go above 90, it's going to start coming back again. So we get 15.8, but we'd have to round down to 15. Your instinct says to round up because that's how you've been taught to round. But we're looking at the greatest value without going over. So in this case, the highest order constructive interference would be at position 15, or of course, minus 15, because it's symmetrical about M equals 0, which would be here. Okay, let's try one final example where we're looking at the slit distance. So we have a third order dark fringe. That's really important because that changes the equation we're going to use a little bit. A third order dark fringe means that we have an N value of 3, not an M value because M is for bright fringes only. So an N value of 3. We have a wavelength of light of 660 nanometers, so 6.60 times 10 to the negative 7 meters. And we have some angle, theta, but more specifically theta 3. It doesn't really affect your equation, but it's just good notation. So if we take a look back at the equations we had before, we need to find something that has theta, lambda, and an N value and solving for the slit width, which is d. So the slit distance is what we're looking for. So we're going to pull out d sine theta equals n minus a half times lambda. If we rearrange this to solve for our slit width, we have n minus a half times lambda over sine theta. And now we can just go ahead and start to substitute values. So 3 minus a half, the lambda value is 6.60 times 10 to the negative 7 meters, and it's sine of 20.0 degrees. What we get here, your calculator will probably give you an answer in scientific notation, 4.8 times 10 to the negative 6 meters. That answer is fine, but it's a little bit more useful to us to put it in a unit that's a little bit better here. Micrometers is a common unit, so we would have 4.8 micrometers.